In this video, I will be going over how to graph reciprocal trig functions along with the tangent graph. And we will be graphing these functions using our knowledge of rational functions. We're going to start with y equals cosecant x. And the first thing we need to note is that cosecant is equal to 1 over sine x. So before I do anything, I'm just going to graph on the side here what sine x looks like, just as a little reminder. We know that sine starts at the origin, and every pi over 2 radians, it jumps special lines. So this is our sine function, and I'll do the opposite on the negative side as well. All right, so here is y equals sine x. From graphing rational functions, we know that vertical asymptotes come from the denominator. So our vertical asymptotes are going to occur when sine x equals 0, because that's what our denominator is. And sine x equals 0 at 0, pi, 2 pi, 3 pi, 4 pi, and so on. So I'm going to put my vertical asymptotes in the exact same spots. I'm just going to write a general equation for all of these vertical asymptotes. So the vertical asymptotes start, if I look at the sine x, it was 0, pi, 2 pi, and so on. And if you use your sequence knowledge or just patterns in general, you'll notice that it's pi and the coefficient in front changes, and the coefficient can just be any integer, positive or negative. So we can say that our vertical asymptotes are at x equals n times pi, where n is an integer. There we are. Next, when graphing rational functions, we know that the x-intercepts come from the numerator when our numerator is equal to 0, but our numerator is 1. So we're actually not going to have any x-intercepts because 1 cannot equal 0. So this is what we're kind of stuck with right now, these vertical asymptotes. Now, thinking of the nature of a reciprocal, there is one value that when you take its reciprocal, it's the exact same value. Actually, two values. And that's 1 and -1. So I'm just going to highlight those on my graph at pi over 2, at 3 pi over 2, and the negative equivalence. Sine is equal to 1 or -1. And if I take the reciprocal of 1, so I'm doing 1 divided by the sine value, it's still 1, which means these are common points. So I'm going to go back to my graph for cosecant, and if sine pi over 2 is equal to 1, cosecant pi over 2 is also equal to 1, because cosecant is the reciprocal of sine at that specific value, which means at 3 pi over 2, we're at -1. At negative pi over 2, we're at -1. And at 3 pi over 2, we're at 1. And now these are the values we have, and we have those vertical asymptotes. So at this point, it's just about me following my asymptotes. Maybe I can use my knowledge of key points to see what the end behaviors are. But if I were to plug in, let's say, a value to the right of 0 to the left of 0, if I plugged, let's say, 0.01 right here into my cosecant or my 1 over sine x, I would get a positive value. Whereas on the negative side, if I put -0.01, I would get a negative number. And I could do that for all of my vertical asymptotes and do my end behavior test, and this is what I would find. It looks like little parabolas between the asymptotes. They're not actually parabolas, but that's what they look like. And there it is. And there is also logic to this part, not just plugging in values to find the end behaviors. But let's say this portion here, between 0 and pi over 2. On sine, from 0 to pi over 2, we are growing. So here, close to 0, these are really small values. And if I do 1 divided by a really small value, I'm going to get a big value, hence starting really big. As I get closer to pi over 2, my values get closer and closer to 1. And when I do 1 divided by something closer to 1, I'm going to get a smaller value. So that's me dipping down. And then from pi over 2 to pi, here I'm close to 1, so I'm going to have lower values. Here I'm closer to 0, so when I do 1 divided by a number closer to 0, something small, I'm going to get bigger and bigger. So these values do make sense when you think about the reciprocal values on the sine function. So a quick recap. For the cosecant function, our vertical asymptotes match up with the zeros on the sine x function, which just end up being n times pi, where n is an integer. And then we know that the max and mins, when they're 1 and -1, the reciprocal is the same. So those are common points. And then we can follow our vertical asymptotes to get our shape. And that's it for cosecant. We're going to do a similar thing for secant, because we know secant is equal to 1 over cos x. So this time on my right graph, I'm going to start with my cos x graph. And cos starts at the maximum, and every pi over 2 degrees, it jumps. I'm going to do it on the negative side as well. And there we go. There's y equals cos x, roughly. Okay, so once again, let's start with our vertical asymptotes. And they are when our denominator is equal to 0. So that's pi over 2, 3 pi over 2, and the negative versions. And let's think about how we can generalize this equation, because we do have an infinite number of vertical asymptotes. So we had pi over 2, 3 pi over 2. If I'm following this pattern, the next one should be 5 pi over 2, and so on. So if I were to try to come up with the equation, it looks like I'm just adding 2 pi to each numerator to get the next vertical asymptote. So we can generalize this as x equals pi plus 2 pi n over 2, where n, of course, is an integer. So that way, over here, if I were to make n 2, for example, I'm adding 4 pi to pi, which gets me to 5. Or if I made it -3, then that's me subtracting 6 pi, which would get me to -5 pi over 2. So this works, and again, I'm just using my patterning knowledge. So now I have my vertical asymptotes. Again, I'm not going to have any x-intercepts because my numerator is 1, and 1 cannot magically turn into 0. This time I will have a y-intercept. Secant 0 is equal to 1, so I actually have a y-intercept value here. But similar to cosecant, the max and mins on cos, so when the y values are 1, will be shared with secant because the reciprocal of 1 or -1 is still 1 or -1. So I'm going to plot those values here. And then we're going to have the exact same style of shape because we have the same motion for cos. So we're going to have the same idea. For example, here, from 0 to pi over 2. On cosecant, we're getting smaller and smaller. And when I take the reciprocal here, close to pi over 2 of something really small, I'm going to get a really big number. So I'm expecting to see this. And then same thing on the left. So now we see that the same shape, just using our knowledge of reciprocals. And there we are. So no x-intercepts, yes y-intercept at 0, 1, no horizontal asymptotes, just like cosecant. And there's our secant function. Next, we're going to graph y equals tan x. And y equals tan x, if we think of trig identities, is equal to sine x over cos x. Well, we already saw our cos function. Looks like this. And we already saw our sine function. Looks like this. And we know our values, so I'm not going to label them, because this is just a mini visual here. So our vertical asymptotes are going to come from when cos is equal to 0. So that's going to be at pi over 2 and 3 pi over 2. And same on the negative side. This time we are going to have x-intercepts, and our x-intercepts are going to come from when sine x is equal to 0. So that's going to be 0, pi, and 2 pi. 0, pi, 2 pi, and the negatives. There we are. And now to actually draw the shape and see how it goes through or approaches these vertical asymptotes, I am going to think about my special triangles, specifically the isosceles one. Because in the isosceles special triangle, our angle is pi over 4, and tan pi over 4 is equal to opposite over adjacent. They're both 1. And the reason I think of this ratio is because the reciprocal of 1 is still 1. So any variation where alpha is pi over 4, so pi over 4, 3 pi over 4, 5 pi over 4, so on, and all of those quadrants, regardless of the rotation, all of those, the tangent will be 1 or negative 1. So that's going to let me graph this here, which tells me, oh, it must mean I'm moving this way. Now at negative pi over 4, well, that would be me in quadrant 4, because I'm rotating backwards, and tan is negative there. So there we are. When we're at 3 pi over 4, which is right here somewhere, we're in quadrant 2. In quadrant 2, tan is negative. When we're at 5 pi over 4, so somewhere here, we're in quadrant 3. Tan is positive there. And here's my shape. And now we're starting to see that these kind of looks like cubic, but it's not. This kind of shape just repeats over and over again. So I'm going to generalize a few things. So our vertical asymptotes are the same as the secant ones. So x equals pi plus multiples of 2 pi over 2, where n is an integer. Our x-intercepts are at multiples of pi. So I'm just going to write n pi comma 0, where n is an integer. And there's our tan function. And if you think of it in terms of sine over cos, it will help guide you where to put the vertical asymptotes, matching it to cos's zeros, and where to put the zeros, matching it to sine's zeros. And then you can draw your shape to follow the asymptotes. And now we're going to do the reciprocal of tan, which is cotangent. So cotangent is equal to cos x over sine x, which means for our vertical asymptotes, we now rely on sine. When is sine equal to 0? At 0, pi, and 2 pi. So I'm going to put my vertical asymptotes there. The x-intercepts come from cosec. Here's cosec. Its zeros are at pi over 2 and at 3 pi over 2. So I'll put those down. And now for my key points, I'm still going to use the pi over 4 because cotangent pi over 4 is also equal to 1, and we're still using the same cast rule quadrants. So at pi over 4, cotangent is going to be positive. At 3 pi over 4, we're in quadrant 2, it's going to be negative, which gives me this shape. Then at 5 pi over 4, we're in tan's quadrant, in quadrant 3. And then at 7 pi over 4, we're in quadrant 4, so we're negative there. And then we get this nice shape, just the opposite direction of the tangent graph. So nothing to memorize here, because you're just using your knowledge of sine and cos and I guess your special triangle in this case. And I'm going to generalize my vertical asymptote. So all of my vertical asymptotes are at x equals multiples of pi. So n times pi, where n is an integer. And all of our x-intercepts are at that pi over 2, and we're adding 2 pi to the numerator. So pi plus 2 pi n all over 2 comma 0, where again n is an integer. And there we go, all of our reciprocal ratios and our tangent ratios, just using the fact that the denominator gives you the vertical asymptotes, the numerator gives you the zeros if they exist, and then using your knowledge of the reciprocal of 1 is still 1. And just that information can get you all 4 of these graphs pretty rapidly with almost no memorization.